Hello everybody, this is Mr. G here. Welcome to engineering. Today we're going to be looking at some truss analysis problems. I know that these truss force calculations can be a little tricky, and I wanted to give everyone a couple of the problems that we do together so that we can all understand how it works. Because once we break it down and we understand what everything means, it's actually pretty simple. You need to have some patience, you need to have a sharp pencil, and you need to be willing to take the time to define all of your terms and understand how the forces are in action. So this video will be nice and long so that we can work through every little bit together so we get a full understanding. If you need to pause the video, if you need to go back, definitely do that. Slow it down, speed it up, whatever you need to do, I'm here for it. Okay, this is problem one. So problem one is a relatively simple truss. You may notice on your handouts that there was a mistake where I forgot to add in, on a couple of the problems, the supports. So you'll notice at point D, there is a fixed support, and at point A, there is a rolling support. That will be important information for you to know later. Right now, I have written up a page of defining the terms. So when you're making force calculations, to determine all of the forces acting in each member, you need to understand a lot of terms that may just be written on the page that you don't exactly know what they mean. So the first few at the top here that I've written out, this is all of your trigonometry. So defining what sine means, what cosine means, and what tangent means. So if you're typing it into your calculator, the sine of some angle. This symbol right here, it's a circle with a line through it. This is the Greek symbol theta. And this little angle here, that is the symbol for an angle. So this is read out on the page. The sine of the angle of theta. So when you pick an angle, say on the page we're picking angle A. So the sine of angle theta, and we know that angle theta is 30 degrees already. So the sine of this 30-degree angle is the opposite over the hypotenuse. So the opposite of the angle would be this guy right here. And the hypotenuse would be the long angle right here. So that is the sine of this angle. So that's something to know. We'll go on to the next one in a second. Okay, now we're going to look at the cosine here. So the cosine of angle theta is going to be the adjacent over the hypotenuse. So if this 30 degrees here is my angle theta, this one right here is going to be my adjacent. So adjacent, opposite, and hypotenuse. Okay, so those are my three sides. So we've got the cosine of angle theta is adjacent divided by hypotenuse. And then last but not least, we have the tangent of the angle theta, which is going to be our opposite over our adjacent. So those are the trig functions that you need to know how to use. You can type them into your handy dandy graphing calculator to give you the answer. We'll get more into that in a second. Okay, the next thing we're going to be looking at is all the symbols that you need to use in your calculations. This letter right here, this is a capital sigma. A capital sigma is the symbol that we represent in mathematical equations for a sum. If you've ever done an Excel document, you've probably noticed this before. But for example, if we're talking about the sum of all the forces is equal to 0, that is the symbol you're going to see. The next thing we're going to look at is the capital M. So capital M stands for moment of force. Now, what is a moment? Okay, I'm going to pull up the definition for a moment of force. So a moment of force is kind of a measurement of torque. So that's kind of the turning a rotational effect of a force calculated as a force multiplied by a distance. It's kind of how a point will rotate, or a force will cause a member to rotate around a point. So that's a moment. And in order to calculate the forces enacting on a truss, we need to understand how to calculate the moment or rotational effect of a force. So that's a moment of force. If you see the symbol capital R, that is the reaction of a support. So in every truss that we're calculating, we're going to have a force acting downwards, and wherever the truss is supported, so for example, we have 450 newtons acting downwards, split across two different supports. So if we have a force acting downwards, we have a reactionary force acting upwards. So this is the reaction at the support, so that would be labeled as R. So in this case, yeah, that would be R. V stands for vertical forces. So all forces in an equation need to equal to 0. So if we have this truss and we have forces acting down and we have forces acting up, the sum of these forces needs to equal to 0. Because every action has an equal and opposite reaction, Newton's third law. So any force acting down also needs the ground to be acting back up on it. In the similar vein, we have horizontal forces. So capital H, if we have forces acting in this direction, we must also have an equal and opposite force acting in this direction. So 1, 2, 3, 4, they all balance out to make 0. And then finally, capital F stands for the amount of force in a member. So you'll notice that I've got in brackets N. So the force acting in a member, which is what we're trying to figure out. That's the end of our equation. How much force is in member AB, how much force is in member AC, etc. So the amount of force in a member is measured in newtons. So newtons of force. Torque is because there's a distance associated with it. So a moment is measured in Newton meters. So how much force over how much distance. So force multiplied by distance is your moment, measured in Newton meters. So kind of review of what we just went over a second ago here. I'm going to scroll down here. For a truss to be in equilibrium, so an equilibrium for a truss to stand, for it to be able to work, the sum of the forces, so the sum, that's that capital sigma there, of the, moments acting on it, so all of the torque, so we often refer to this in class as the shear force acting on joints, so the sum of the moments acting on it, as well as the sum, there's that capital sigma again, of the forces, capital F, in both the horizontal, H, and the vertical, capital V, directions, all of those things must equal to 0. 0. So no matter what you're calculating, all your calculations, if you compute the forces opposing each other, must equal 0. these can simply be written as the forces, or the sum of the moments, the sum of the moments is equal to 0. The sum of the forces that are horizontal is equal to 0. And the sum of the forces that are vertical is equal to 0. Okay, now let's try and put that into action. All right, so to start our equations, we are going to start to define some pieces on our diagram here. So the first thing we need to start looking at is the directions that our forces are being acted on. So on this truss, we have 450 newtons of force acting directly on both of these supports. On a fixed support, where it has no ability to roll, we are able to directly start to look at the horizontal forces and the vertical forces. And on the other side, on a rolling support, it's not confined by having any torque being put on it. So it kind of can just react against the raw amount of force that is pushing on it right here. So if we are starting our equation, we know that the sum of the moments around point D, this is point D, the sum of the moments around point D must equal to 0. So whatever the force is coming down this way, vertically, whatever the force is going this way, horizontally, must all equal to 0. So if we start out with at C, where the amount of force is being enacted on the bottom of the truss, that's kind of equal in its vector, perfectly perpendicular to these two, we can write our equation that 2 multiplied by the reaction at the supports, or 2 times R. In this case, we're going to look at A because it's rolling, is equal to 450 newtons. So this is going to give us the opposite reaction of this force coming down at point RA. So the reaction at point A right here. Because it's rolling, it can be directly opposite. So what this will do for us, if we divide by 2, RA, so the reaction of the support at point A is going to equal to 225 newtons. Okay, if we continue on along here, we got to the fact that the sum of the moments around point A needs to equal 0. So if we have, I've just made the lengths of each of these lines right here. That's going to be my x. For sake of argument, we're going to just say x is equal to 1. Because we don't have any distances on any of the lengths of anything, it doesn't really matter what value you put in there. It will all kind of work out to be the same because it's a ratio. But we'll just say anytime you see x, it will be equal to 1. So because we have 2 lengths, so 2x, or 2, of the vertical forces around point D, we will have 450 newtons, so 450 newtons acting down, plus we also have 450 newtons on this point acting at the sine of a 30-degree angle. So, and that is split over our 2 different members there. So if we start to boil this down, if we do 450 sine of 30 degrees, that is going to equal 225. So now we have 2x is equal to 450x plus 225 times 2x, Simplify it again. 2x is equal to 450x plus 450x, which then we would have 2x VD is equal to 900x. And if we divide by both sides, we get VD is equal to 450x. So now, if we go back over here, on our rolling joint, we have 225 newtons resisting the forces this way. And on our other side, at VD, we have 450, and we can exchange X for 1 newton. 450 newtons resisting the force is downward in the vertical direction. So 450 newtons. So we're starting with this and with this. So once we've calculated the moments working around each joint, we can start to look at the forces in individual members. Okay, so sorry for the pause there, just kind of going over my notes. So we have gotten the moments around point D and point A figured out with the force in newtons, 450 newtons pushing at a 30-degree angle here, and a force of 450 newtons pulling down from point C. So now we're going to start taking a look at the sum of the forces in the horizontal direction, or the forces in the members in the horizontal direction. So right here across the bottom, because it's one straight member, there's no kind of angle of compression, and it's across 2 points, there's no ability for it to rotate. So instead of looking at the moment of force, we can just straight up calculate the forces in the members. So again, the sum of the forces for the horizontal direction, the sum of FH, we know that all of it together needs to equal to 0. So that's our formula, same as up here. The sum of the moments need to equal 0. The sum of moments need to equal 0. The sum of the forces in the horizontal direction need to equal 0. The sum of the forces in the vertical direction need to equal 0. Everything equals 0. You get a 0. You get a 0. Everyone gets a 0. Okay, so if we are looking at this, we have the sum of the forces is equal to 0. So we're gonna look at trying to figure out the next part of the equation here. So hold on just a second, let me check my notes. Okay, so what we need to do is kind of find the force in the members of this one right here. And so because point D is our fixed point and we're trying to find the force in the member here, and our 450 newtons is acting down, we are going to be looking at our horizontal forces from point D are going to equal to that 450 newtons to the cosine of 30 degrees. And if we look over here, the reason why we're doing this is, what's cosine again? Cosine is adjacent over hypotenuse. So we have our adjacent over our hypotenuse, because we're trying to find, and we've got the force acting on the opposite. So that's what we get there. Okay, so if we have 450 cosine 30 degrees, if you type that into your graphing calculator, that is going to come up with 389.71 million decimals repeating. So we're going to cap it at 2 decimal points there. And we measure in newtons. So we have our horizontal force around point D is 389.71 newtons.